Okay guys, so we talked about reflection and now we'll talk about refraction. And in reflection we discussed reflection through plane surface and reflections through curved plane mirror and curved mirror. Here we will talk about refraction through plane surface, plane medium or curved surface, and then finally lenses which are made of two curved surfaces. Okay, so just to reiterate, in capsule course, like in this session, I presume that you guys have gone through one round of reading of chapter through a book or through my previous sessions, right? And here my objective would be to make you learn all derivations uh, so easily that it lasts in your mind for a longer time. Rather, every time you think about derivation and you get nervous, right? You get panic, or before exam you need to revise so many things. So, and derivation actually makes your concept all the time very clear, right? That we talked earlier also. So, on refractions in general, if you know, light travels straight, but when it hits any medium, right, then it takes a different path which may be at certain angle. Okay, so we have, let's say there is a, this is little denser medium and this is lighter. You can call it 2 or D denser, you can call it 1 or R lighter medium, rarer medium, we call rarer and denser. Okay, and a light ray is falling like this on a medium, and now let me draw a perpendicular here at this surface. So as it, what has been observed, when light travels from a rarer medium to a denser medium, it bends towards normal at that point where it has hit the surface. So light will go like this, okay? If you call this as angle of incidence, this as angle of refraction, not reflection, okay? And then if you take it, then this you can, this is no use, but this you can say a displacement D. Okay, so light has displaced by its original path by angle D. So that is the behavior is observed. Okay, and those are two, those are defined, those two items which we'll talk about are actually called laws when we define this refraction. Okay, the first law of refraction is angle of incidence incident ray, refracted ray and normal, all three should be at the same plane. Same thing we learned on mirrors, right? Reflection. So nothing new, you can always remember. Second, in reflection we said angle of incidence will be equal to angle of reflection. Here they say sine of angle of incidence I divided by sine of angle of refraction R is a constant. So that was, they took so many observations and they found always this is a constant, right? And later on that constant was defined as a refractive index of second medium in reference to first. Okay, so that is a constant. Now you can ask why light bends towards normal. Okay, so we need to go back to something properties of light, very basic Huygens principle, then we'll come to know. But in short, I can tell you, actually the light's behavior of turning towards normal or getting away from normal happens because of difference of speed in medium 1 and medium 2. If it's the same medium, then it will not change its path. Okay, and it is found that sin I by sin r equal to v1. v1 is velocity, speed of light in medium 1, which you can call rarer or denser, whatever in your case, and then v2, the speed in second medium. All right. So now we know sin I by sin r equal to v1 by v2, and then that constant was defined as refractive index of 2 with respect to 1, and we write it 1 and 2. Refractive index of 2 with respect to 1. Okay, so that's a way we define refractive index. Now you assume that one medium is vacuum and another is any other medium, which we call let's say medium, just we call any medium, right? So in that case, sin I divided by sin r, right, or will be equal to c divided by v, and in this case this refractive index would be called just refractive index because it is with reference to vacuum or air, right? I mean, we take both of them as the same, right? And we just denote as a n. And then when we say n, refractive index of medium with respect to air or vacuum. Okay. So C by V equal to n. Very simple thing to learn and remember. Okay. So based on that, we will prove. So we learned about this now, V1 by V2, and we learned about now we have to prove that between any medium, let's say for the time being you assume this is 2 and this is medium 3. Okay, so if we have to find refractive index of 3 with reference to 2, we have to write V3 divided by, V2, right, divided by V3. Keep in mind so that you don't forget whatever first medium from where ray is coming, we need to write velocity of that on the top and bottom, the medium where ray of light is entering into. Okay, or if we write this as C, just multiply both top and bottom, numerator and denominator by C. So we can write C by V3 equal to C by V2, isn't it? And C by V3 we know, right, it would be N3 because N3 refractive index of medium 3 with respect to air or vacuum. So we can say N3 divided by N2. Okay, so that's what I have written here. So now we know two formulas. I'll just explain I'll just go through one more time so that it's easy for you to remember. If I say 2 and 3, then you have to write on top N3, right, because it with respect to, and we always, when we have to say in reference to something, we we keep that as a in bottom, we divide by that, right? So n3 divided by n2, very simple. Okay, so we proved that these two things, right? Now, so two laws we know. Now I want to prove that one important property which is derived by these two formulas, that if you put a plane mirror here, it is said that the light will be reflected, right? We are putting a plane mirror just perpendicular to that ray of light. Then light will be reflected here. It will take its own path, and when it hits back at this point, it will go again following the same path it has taken while entering into the medium. This is called reversibility of light. Okay, so, and you can prove that. Simply by, if this is sine by sine I by sine R, right? And if I say, because in different in the reverse path, we have to write sine R, because R is same. We have put a plane mirror where it reflects light back, right? R would be same, but we don't know what would be the I. So we have to prove that. I would say sine I dash. Okay, and this would be refractive index of 1 with respect to 2. With respect to 2 and 1. Okay, 2 and 1. And we just now we learned, by C by V, with the C by V, that 2 and 1 would be nothing but 1 and 2. Okay, so now we can say sine I dash divided by sine R equal to 1 and 2. So we came back to the same. It means I dash and I would be same. So we proved that reversibility property of light just using this refractive definition. Now there's one more property which is derived from this basic formulas. Okay. Let's say there are multiple layers of different mediums and plane mediums. So you assume 1, 2, this is medium 2, this is medium 3, this is 1, this is 1. You can, so here, sorry, it will take time. So let me draw. Okay, this is your eye. So we'll assume that this reflects here, and then when it falls here, it will again bend down, and then it will go out. So what it says, that when light enters through a multiple layers of medium and finally it goes to same medium, it will follow the same path. I mean, the direction angle will not be changed, but there would be a displacement. Okay, so that's what we have to prove. So you can remember this, right? If you take through multiple mediums, finally light will be straight, parallel to the original path, but with some displacement. very simple. Here I would be angle of incidence, this would be R, but this normal and this normal, they are parallel lines and this is intersecting lines. The next I would be equal to R because of those are alternate angle. If this is R, then let's say this is your R1. If this is R1, then again next I would be R1, okay, and finally we will assume that this one, your angle of final angle of refraction is I dash, okay. So again we have to prove that I dash would be equal to I, and we know, so for first medium you can say sine I divided by sine R equal to 1 and 2. Next, for next medium, when light is coming on from, light is hitting the medium 2 and 3 surface, like this point, angle of incidence would be R. So we can write R, okay, and angle of refraction, we assume it is sine R dash, okay, would be 2 and 3 because refractive index of 3 with respect to 2. So we wrote 2 and 3. R will be equal to R, reason these are two parallel lines, no, they are normals, and this is your intersecting line. For third case, R dash would become next I, angle of incidence. So sine R dash divided by sine I dash equal to 3 and 1. Okay. If you multiply, so we just applied these two, one formula, basic formula at three places whenever light hits a different medium. If you multiply all these three, right, then sine R will be gone, sine R dash would be gone, right. Only thing would be left is sine I divided by sine I dash equal to multiplication of all these three. So 1 and 2 multiplied by 2 and 3 multiplied by 3 and 1, right? And some time back we just proved if 1 is air, suppose, right, that 2 and 3 is equal to n3, like 1 and 3 divided by 1 and 2, 2 and 3, right? So we will write 1 and 2, 1 and 3 divided by 1 and 2, okay, and we know that 3 and 1 is equal to 1 by 1 and 3, so 1. That proves that I and I dash would be same. So people take it different ways. Sometimes they say that these are property of light, and you know, and by doing that they will say sin I by sin I and I dash would be same. So 1 and 2, 2 and 3, 3 and 1, you know, multiplication of all those will be 1. And we proved here reverse way because we know that 2 and 3 is equal to n3 by n2 using the formula of velocity. So you can use either way, no issue, but just you need to understand. It's a very simple that you need to understand. There would be multiple layers. You keep on multiplying the refractive index of first medium with respect to previous one, and when you reach at the last, right, and make it equal to 1. So with the help of these three formulas, we understood the basics of this, right? Now we will prove one more thing, which is called total reflection. Okay, which is called total reflection. This is normal. This is a ray which is falling at this point O, and it bends, sorry, it goes away from the normal. Okay, this is your rarer medium, this is your denser medium. As just now we learned that when lights enter from rarer medium to denser medium, it will bend towards normal. But if it enters from denser to rarer, it bends away from the normal. Right? That is what I showed here. So angle of R would be more than angle I if it is going from D to R. So what happens if you keep on increasing I? If you keep on increasing I, there would be an angle C, whatever angle, I mean we will name it C now for the time being. There would be an angle C where a light would be just reflect. I mean, it will not enter into the second medium, rather it will take the path along the surface. So that particular angle is called critical angle. Okay, so definition of critical angle: when light enters from denser medium to rarer medium, the minimum angle at which complete light gets reflected along the plane surface, that is called critical angle. Right? It will automatically happen. You know, if you keep on increasing angle of I, it will get reflected. There are many use cases, but I hope you can read through your books, right? So again, I will use the same formula. I would say sine, in place of I would put C divided by sine of angle of reflection. But now for that particular case, R would be 90 degree, right? You can see that this would be 90, equal to, please make a note, it is refractive index of R, the difference to D. So we write D and R. That is all. Sin 90 is 1, so sin C equal to D and R. No need to mug up anything. Whenever you get, you have been asked some numericals or about critical angle, you have to know, you just apply sin C divided by sin 90, but you have to keep this in mind that total reflection, this property is called total reflection, happens only when light is entering from denser to rarer. So you have to write D and R. But what happens, generally R is taken as air, right? So we call it, refractive index of air with respect to D, which could be glass, water, anything, right? And as we know that it is reciprocal of, D and R would be 1 R and D. So sometimes we say sin C equal to, if R is air, then we call just 1 by n. So people remember by this also, but I think simple and with more concepts, you need to see this one. Okay, but again, here we are saying D and R, and when we say 1 by n, we assume that another one is just A. Okay, so we talked about critical angle also, at which total reflection happens, and there are applications that, you know, if you you will see something and you put in your glass, you will see it's you know, it looks thin, very shiny. Let's go through that later on. Actually, we have already covered in our previous sessions. Now we are going to the last formula, which is used here in this chapter to solve numericals and again to explain our day-to-day, you know, application of this property. Like if you put a rod in water, you will see your rod is little, you know, bented towards up, right, and height looks a little shorter. Okay, and we call similar, you know, we study that a ghost fish, right? So if a fish is inside water, which is a denser medium, and you're looking at it, so actually you will see that fish actual height, not height, depth is more than where it seems to be present at that time. Very common, everybody knows about it. But what happens, generally the questions are asked, what is apparent depth? Okay, so what would be the apparent depth of any object if it is in a denser medium? Remember, don't get confused with water, and you have to remember, when light, anything is in denser medium and you are viewing it from a rare medium, the height would be apparent height, not the real height of. So how does it happen? Let me draw a diagram. Okay, this is normal as we take always, and there is an object at this place O, and sorry to not able to draw. Okay, this is O. So ray of light coming from O, it's hitting at C, and this is your normal, and then it goes like this. But if you trace it back and then draw a perpendicular line, which is nothing but another ray of light. As you know, to find image of anything, we need to have two rays of light. So let's say one ray of light is going like this, another ray of light is going perpendicular to this, so it will go straight. Okay, and where is viewer's eye? It is, let's say, here. Okay, this is eye. Not necessarily we have to take this ray. I can prove if we take another ray like this, still I can prove that concept, right? I mean that formula. So let's say this is O dash, this is your M. Now, so if total depth is D, this would be called dA, because to viewer actually the object appears to be here, which is less than D. Now we have to formula, the formula will result as we wrote on the top, but we'll prove that. So in this case, this is your I, angle of incidence, this is your R, and because these two are normal, so this angle would be equal to this angle, I, because it's alternate angle, and R, this R would be opposite angle, right, to this, you know, what do you call this one? Yes. this, it would be like this. Not opposite actually. These are your corresponding angle. I don't know whether you can see it. These are two parallel lines, and this ray, which we have traced it back, right? So this ray is intersecting line. So this angle would be this angle, R. Very simple. We are just using geometry. Okay. So you need to remember these two angles. And now you have to look at two triangles, triangle OMC and O-MC. You have to look at these two triangles. Okay. So in this case, our sine I divided by sine R equal to, this is your denser medium, this is your rarer medium, D and R. Then only light will be going away from the normal. Okay, would be D and R. D and R. Now if we put sine I in terms of perpendicular divided by hypotenuse, so it would be MC divided by OC, and then R, similarly R MC for this triangle O-MC, MC divided by your O-C, which is MC can be D and R, so which becomes O-C divided by OC equal to D and R. Okay, and now what we have, there are always some caveats, right? And those caveats you have to remember. In this case we say if the aperture of I is small, then O-C can be taken as OM, and OC can be taken as OM, and O-C can be taken as OR. Actually that happens because whenever if you look at I, somebody would be looking like in the I aperture would be very small. So in that case we say O-M equal to OM is nothing but D into D and R, and we can write, because R is generally air, so we don't want to write D and air, rather D and A would be A and D, which is nothing but refractive index of medium. So we call D divided by 1 by R and D. So looking at formula, we got that formula. D apparent depth would be original depth divided by refractive index of denser medium, or original depth multiplied by refractive index of rarer medium with respect to denser medium. Generally, denser medium's refractive index is more than 1. That is the reason if you divide D by R and D, it would be more than 1. So D is lesser than D. Very simple. Whenever these kind of numericals are asked, you just need to remember one thing: apparent height would be lesser than real height. I should use depth, right? Sorry, depth. If rays are coming from denser to rarer, and that happens when you divide actual by refractive index of that medium. And we assume that it is air, but if it is not air, then you have to be very careful. You have to take refractive index of denser medium with respect to rarer. So another example which is very interesting, that if viewer is inside water, viewer's eyes are inside water, maybe it's fish or anything else, and it is looking at an object which is outside of water, then the real height would be lesser than the apparent height. Means if the guy is who's standing 5 feet, and he will look like 5.5 feet or something like that. Okay, and how do you see that? Assume for the time being, that these rays, if I change the direction, right, they are coming from rarer to denser. Okay, and eyes are somewhere here. So what happens? Your ray would be refracted and would be bending towards normal. And if you extend it here, it will seem like that these rays are coming from here. So the real height would be this, and this would look like this. So a different example. In that case, you have to multiply. You have to multiply to find apparent height, not apparent depth. You have to multiply dA equal to, not HA equal to H multiplied by refractive index of denser medium. Same thing you can prove on your own. Okay. So this is all for plane surface, and now let's talk about curved surfaces. Okay, thanks.